All right, let's talk about math. We all tend to think of it as this fortress of absolute certainty, right? The one place where things are either true or false. But what if I told you that deep down, at its very core, there's this huge philosophical war going on, a battle for the very soul of mathematics? And that's exactly what we're jumping into today.
So let's just get right to the heart of it with the one question that changes everything. Is math invented or is it discovered? I mean, think about it. When a mathematician comes up with a new theorem, are they like an astronomer spotting a planet that was always there, just waiting to be seen? Or are they more like a chess grandmaster, inventing a brilliant new move in a game with rules that we made up? Seriously, this one question, it's the key to this whole story.
Okay, picture all of mathematics as this gigantic, incredible skyscraper. For that whole thing to be trustworthy, for every single floor to be safe, you need a foundation that is absolutely rock solid. No cracks, no weaknesses, nothing. But what is that foundation actually made of? Well, for over 100 years now, the math world has pretty much settled on an answer: set theory. Yeah, it sounds simple, the idea of just grouping things into collections, or sets. But it turned out to be so powerful that you can build almost everything else in math right on top of it. Numbers, shapes, you name it. It became the bedrock.
But here's the twist. That bedrock, it is not a peaceful place. It's the central battleground for that exact question we started with. The whole fight over whether math is discovered or invented, it's happening right here, at the very foundation of it all.
So let's get to know the two major players in this conflict. They have completely different ways of looking at the entire mathematical universe. So on one side, you've got the realists. You might also hear them called Platonists. These guys believe that there's a real abstract universe of mathematical objects just out there, independent of us. And mathematicians, they're basically explorers charting this hidden reality. Then on the other side, you have the formalists. They say, no, math is just a really sophisticated game. As long as the rules we make up are consistent and don't contradict themselves, that's all that matters. There's nothing out there to discover at all. So for a realist, the most important thing is that mathematical truth means you're correctly describing this special, abstract reality. Take George Cantor, for example. When he started doing his groundbreaking, totally mind-bending work on different sizes of infinity, he wasn't just playing a game. He absolutely believed he was discovering timeless, fundamental truths about a universe of sets that actually existed.
Now, the opposition, the anti-realists, they see things very differently. We've already met the formalists, right? For them, consistency is the name of the game. But they're not alone. You've got the intuitionists, who argue that math is something we literally construct inside our own minds. And then there are the nominalists, who take it even further. They say abstract objects like the number 7 don't exist at all. Math is just a really useful language. But you see the common thread, right? For all of them, math is fundamentally a human creation.
Okay, so you're probably wondering, how on earth does any math get done if everyone is arguing about what it even is? And that's a fair question. Well, the community came up with a really practical solution: a shared rulebook, a set of rules everyone could agree to play by, no matter what they personally believed about the nature of the game. And that rulebook is called ZFC. It's basically a collection of axioms, these fundamental assumptions that act as the starting point for building the entire universe of sets. The best way to think about it is like the official operating system for all of modern mathematics. See, early set theory had run into some, let's just say, shocking paradoxes that threw everyone into a bit of a crisis. ZFC was designed to patch those holes, to fix those cracks, and to give everyone a stable, consistent foundation to build on. It let mathematicians get back to work without having to first solve the ultimate philosophical riddles. And for a while, it really seemed like this new operating system was flawless. But then a discovery was made, a discovery that didn't just shake things up. It shook the very idea of mathematical certainty to its absolute core. It proved that even the best rulebook has its limits. The year was 1931, and a young logician from Austria named Kurt Gödel was about to publish a paper that would completely change our understanding of what math can, and more importantly, cannot do. This is where Gödel drops a total philosophical bombshell. He mathematically proved that in any powerful and consistent system like ZFC, there will always be statements that are true, but that you can never, ever prove using the rules of that system. Let me say that again. He showed that truth is bigger than proof. The search for a single, complete, final rulebook for all of math, it was officially over. And this wasn't just some obscure technical point.
It was a philosophical earthquake. It proved that any formal system we try to create is going to be, by its very nature, incomplete. The dream of capturing all of mathematical truth in one neat axiomatic package was suddenly and provably impossible. And Gödel's discovery was really just the beginning. It turned out other huge, crucial mathematical questions were also independent of ZFC. So what does that mean? It means you literally can't use the rules of ZFC to decide if they're true or false. You could add an axiom saying one of them is true, or you could add an axiom saying it's false, and either way, you'd end up with a perfectly consistent version of mathematics. It's like a choose-your-own-adventure at the very heart of math. But here's the amazing thing. This didn't kill mathematics. Not at all. In fact, uncovering these limits cracked the door wide open for completely new ways of thinking about what the foundations of math could even look like. With ZFC shown to be incomplete, people started developing totally new foundational systems, each one offering a different vision of the mathematical universe. You could say the race for the next great operating system for math was on. One of the major challengers is something called category theory, and it's a really radical shift in thinking. Instead of being obsessed with what mathematical objects are, category theory is all about the relationships and the structures between them. Think of it as a math of arrows and connections, not just a collection of lonely dots. This focus on structure makes it incredibly useful in fields like computer science and modern physics. Another really powerful contender is type theory. It comes from logic and computer science, and it provides a completely different way to build up all of math. It works by sorting objects into different types, kind of like how you'd organize data in a computer program, and that creates this really robust, really versatile foundation. In fact, this is the very idea behind software that can automatically check mathematical proofs for mistakes, which is just incredible. But here's the real kicker. None of these new, fancy systems actually solve the original philosophical problem. They just move the battlefield. People who champion category theory or type theory are still having the same old argument. Are we discovering a deeper layer of reality, or are we just inventing a better, more powerful game? The debate just continues. And that brings us right back to where we began. If the very bedrock of what we think of as our most certain form of knowledge isn't a solid rock at all, but an ongoing philosophical debate, a choice between different ways of believing, well, what does that mean for our idea of certainty itself? It seems the answer isn't a number. The answer is just a bigger, deeper question.